Okay, so then I'll continue the story I started yesterday, repeating some parts. So my plan had been yesterday to talk completely about the case of graphs, and today about the case of Hurwitz numbers, emphasizing the similarities. But in fact, I'll be forced to emphasize them even more because I didn't quite finish. And so I have to give you the last part yesterday. So let me remind you the three main ingredients of what I'm talking about are GGD, which is the number, I'm not going to go into again, it's the weighted number of graphs counted with 1 over the number of automorphisms. And a graph is, of connected graphs, but with no other restrictions. So the edges are not oriented, but there can be multiple edges or loops or anything you want. Okay, with D vertices and G independent cycles, or first Betti number G. HGD, which I'll talk about today and define carefully, is the number, again weighted in some suitable sense, of coverings. And this is, again, you have a surface of degree G covering the surface of G degree 0, so the true sphere, and this is D to 1 and generically ramified. So those are the Hurwitz numbers I'll talk about later. And the statement was, there were several statements, but one was that if you fix D, then GGD or HGD, so I proved it for G and I'll prove it today for H, is an elementary function of G. So it's a sum, a finite linear combination of pure exponentials. So things like, 9 to the G. So it's a fixed rational combination of a finite number of purely exponential functions. And that's true for both H and G. But if you fix G, then these functions, well, now you have to be a little careful. You have to divide them, multiply them by d factorial because there's a denominator. Well, they belong to what I call the extended Lambert space, which is a certain space of sequences. So those were the two main claims. This is rather elementary, but there are several points of view, and it's quite fun. For the Hurwitz numbers, that was done by Hurwitz himself in his original paper of 1891, I'll come to. But the other part is more fun. So let me remind you of the Lambert space, which I talked about. So the Lambert space I call lambda, and there will be an extended one which contains it with infinite codimension. So extended Lambert space. And here, in both cases, we actually almost never need the extension. We only need it if G is very small, if it's 0 or 1. There are some exceptional cases, so we don't need the whole extended Lambert space, but only a very small extension that contains lambda with codimension, in fact, 4. So the main thing was this, which was also a ring, so I can also call it the Lambert ring. And there were many ways to points of view, but the easiest, and I'll remind you just very quickly how that went. Lambda is a subset of what I called script A. I won't use this again, but it's convenient, which is functions from the natural numbers to Z, so integer valued sequences, but then tensored with Q. So it means they're rational valued sequences, but with a fixed or a bounded denominator, so the whole sequence. So this is a subset of simply all polynomial sequences of rational numbers, so all functions from the natural numbers to Q. And each of these things is a ring with respect to star, and then this was less trivially a ring. I'll remind you the definition in a second. So each of these are subrings, so you have a multiplication, and the multiplication was the convolution if I have two functions, f and g. So f and g are functions on positive integers with rational values. In fact, they will have, in these two cases, they'll have bounded denominators. then f star g is simply the sum binomial coefficient f of e, g of d minus e, where e is strictly between 0 and d, because I don't want to allow 0. Anyway, for these degrees and so on, you don't really get degree 0. Okay, so that was the definition. And a more intelligible definition is you send f to f bar, which, to remind you, the name of the indeterminate is f bar z, but it's not a function, it's a formal power series. And this is just the generating series, f of d or f sub d, I kind of use them interchangeably, z to the d over d factorial. So this is a map from q to the n and also of these subsets. But the map from all of q to the n is an isomorphism with all formal power series where the constant term is 0. That's sort of trivial, because if you have a power series, you just take the dth coefficient and multiply it by d factorial. And then you're just clear by Cauchy multiplication that this corresponds to the multiplication. So here, if f and g are two functions, then f star g bar is simply f bar times g bar. So it's just ordinary multiplication, and it's usually more convenient to think of the function t. But I want to think of lambda primarily as a collection of sequences, because the generating function, useful though it is only a helping, an auxiliary tool. And the last thing was that we also had d corresponds to d, where on the side of q to the n, d is the map. D of a function, if f is a function on the natural numbers, then df of d is just the function where you multiply f of d by d. So you can take any polynomial in capital D, apply to f, and it just means you've multiplied your sequence of numbers by some polynomial in D, which is kind of a trivial operation. So if I know a sequence of numbers, some complicated sequence, I certainly know the sequence d squared minus 3 times that original sequence. So this is kind of an elementary thing. And so that's what d is on this side. And on this side, d is the differential operator z by dz, which of course exactly sends the dth coefficient to d times itself. So we have that. Oh, somebody's telephoning me. Well, they're out of luck. I'll have to find some other. Maybe I'll even turn it off if I can remember how. Yeah. Okay. If somebody calls you, feel free to answer, but I somehow shouldn't. Okay. So that was the background. And now lambda was simply, although this was an artificial definition, but still you can take it, it was generated by two specific sequences, which you could either define by a characteristic property of the generating function or recursion, or by closed formula. I'll repeat all three in a second. And so this just means that it's a typical function here has the form p of d times, so every function, any sequence in lambda has the form p of d times alpha of d. Alpha, I'll remind you the definition in 1 second, plus q of d times beta of d, which I'll also remind you in 1 second. And these are arbitrary polynomials with rational coefficients. So in other words, if you know alpha and beta, you know everybody. And I also can choose a basis of this space. So the basis is then obviously alpha n beta n, where n is greater than or equal to 0. And alpha n is by definition d to the n of alpha. Beta n is by definition d to the n of beta, which again means that alpha n of d is just a, I don't want to always write the d, so I need to put the index, but it's nothing more nor less than alpha of d times d to the n. Okay, and similarly for beta, of course. Okay, so that's a basis. And then the functions were given in two ways. So explicit formula was alpha of d is simply d to the d. That's very explicit. And beta of d is d factorial times, and then you take the expansion of e to the d. So the usual Taylor series of e to the d, which is the sum r from 0 to infinity, d to the r over r factorial. And then you observe that as r grows, the terms increase strictly until r equals d minus 1. Then the next term, r equals d, is equal. So they increase, then 2 are equal, and then they decrease. and we take all of the ones up to the first of the two equal ones. We take kind of half of the series for e to the d, and that's the closed formula that is I just write it for fun, but I'll actually never use it, except to notice that from this formula it's obvious that this is divisible once by d, right? Because d to the r is an integer, and divisible by d, but I don't even care. D factorial over r factorial is an integer because r, but it's that d times an integer, because since r is less than or equal to d minus 1, you would only need a d minus 1 factorial to kill the denominator. So, and I have an extra d. But I don't have an extra one because by Wilson's theorem, I guess, if d is a prime, then you find that this number, if you divide it by d, by p, it's minus 1 mod p, so you can't divide a second time. Okay, so the extended lambda ring is generated by beta minus 1, well, by beta n, well, alpha n, n in z, and beta n, n greater than or equal to minus 1. And it's actually not a ring because beta of minus 1, its square, for instance, is not in there. The other part you can include, and I wrote out that proposition last time. I won't repeat it. So this is the point of view just by giving the sequences explicitly. That's just, so to speak, in closed form. But a better way to do it is alpha bar of z, well, actually alpha minus 1 bar of z, which, according to what I just told you, is d to the d minus 1 over d factorial z to the d as a power series in the indeterminate d. This is what I will usually denote by t of z. Okay, and t of z is defined, so let's just call it t. It's defined by the relation z is t e to the minus t, which, as I showed last time, you can translate into a simple recursive formula for the alphas, so you can also just calculate alpha and similarly beta directly. I think the formula was alpha minus alpha star alpha minus 1 is alpha minus 1. So if you take this formula that uniquely determines alpha, and if you say alpha minus 1 bar, you just call it t, then this equation turns into saying that d of t is t over 1 minus t. And so it means is that our d, which was a differential operator, which is a derivation either with respect to here, but then it's also a derivation here, which you can check directly from the definition. If you apply capital D to f, you multiply by e. When you apply to g, you multiply by d minus e. If you add those, you've multiplied by d, which means adding it here. So it's obvious here also that this d is a derivation, but it's also obvious because this is an isomorphism, and so it preserves any structures that are going. Sorry, this is star. So we have this derivation d, and you should think of d as just an abstract object. It's simply something you can apply. It's not really z by dz. That's what it is in this representation. But in this representation, it's multiplication by d. And in the representation as functions of t, of course, power series without constant term in z is the same. It's canonically the same as power series without constant term in t. It's not isomorphic. It's the same because t is in the thing on the left and vice versa. They're simply the same. And so I can equally write t there. And then the formula that we need is this one, which is exactly what you get from here. So you can think of this d as a derivation in the different things, and don't think that it's really this, and that's just a translation. It's really each of these. It's a derivation, and from each, in each realization of this ring, you have a different formula for it. So that's the basic story. And so now, as I said, alpha minus 1, I'll drop the bar. I'll just call it alpha. Alpha minus 1 is t. Therefore, alpha is d of t, which is t over 1 minus t, because you apply this differential operator t. Alpha 1, if you care, is d of t over 1 minus t. The derivative of t over 1 minus t is the same as 1 over 1 minus t, so it's 1 minus t squared, but then I have to multiply by another 1 minus t, and by t, so I get this. And then as we saw, alpha n is a polynomial, if n is at least 0, of degree exactly 2n plus 1 in 1 over 1 minus t. So that's alpha. And if you do it for beta, well, actually, the nicest one is beta minus 1, because beta minus 1 is still an integer. That's the one that I gave you a little table. Those are kind of the nicest numbers. So n and beta minus 1 of n, d I guess I'm calling it. It started 1, 3, 17. I don't remember after that, but I wrote them several times yesterday. So that's some very nice sequence. And as a generating function, well, if I put the bar to be correct, it will be, so this is by definition the sum beta of d divided by d, z to the d over d factorial. That's the definition of the bar, right? Because beta minus 1 is beta of d over d. But in terms of t, this is log 1 over 1 minus t. And the reason for that is then applying d. You find that beta itself, or beta bar, well, you have to differentiate that. That's 1 over 1 minus t, and then multiplied by t over 1 minus t squared. And so that's beta bar. And similarly, if you continue, then beta 1 bar, as I say, I'll usually just drop the bar. We'll identify a sequence in the power series. Beta 1 bar is then t plus t squared. If you just apply the differential operator d by dt to this and multiply by t over 1 minus t, then you'll find this. And in general, beta n, for n positive, is a polynomial of degree exactly 2n plus 2 in 1 over 1 minus t. And so we see that under this isomorphism, f goes to f bar, lambda is isomorphic. Since this is an isomorphic image, I'll call lambda bar, which is simply all polynomials in 1 over 1 minus t which vanish at 0. Which, since a polynomial in 1 over 1 minus t is the same as a polynomial in t over 1 minus t, then it's just polynomials in t over 1 minus t without constant terms, so it's also that. So in particular, it's a ring, and that was the proof that it was a ring. Okay, so that was a reminder. All of this I did yesterday. This was a reminder. It's meant to be very elementary. I'll stop talking for a minute so you can take notes. And you can ask, now's a good time to ask any questions about what I've said so far. So in particular about these. I can't hear you. Well, I just defined a space, yeah? Well, that's the definition. This is the definition. The definition I chose is lambda is the free Q of D modulo spanned by two things, alpha and beta. I didn't give an intrinsic definition. So by definition, that means that a sequence is simply alpha of D times a polynomial plus beta of D times another polynomial. Or equivalently, since every polynomial is a sum of monomials, D to the n, and so is this, it's a combination of alpha to the n and beta to the n, which are these. So I just defined it. I've listed a countable sequence of sequences, alpha, so you should think of them in order, alpha 0, beta 0, alpha 1, beta 1. Really, they should be numbered 1, 2, 3, because the degree, remember, of alpha 0 was 1. The degree of alpha 1 was 3. The degree of alpha 2 was 5. But the degree of beta 0 was 2. The degree of beta 1 was 4. So the canonical order of the base would be alpha 0, beta 0, alpha 1, beta 1. And then under this isomorphism, it's simply some complicated collection of polynomials, but they're a perfectly good basis because each one has a strictly bigger degree. So it's a basis for polynomials. And in particular, you get the polynomial ring, which we all know is a ring. Even though it's by no means obvious what happens when you multiply alpha 16 with alpha 19 and write it as a combination of alphas and betas. It's some total mess. So it's not an obvious base. The structure constants are not very easy to compute, but luckily we don't need them. At no point do I know anybody who actually multiplies two of these sequences. So the fact that it's a ring is actually just for fun. I'm not going to use it. What I will use, however, is that it's a free Z module, that it's generated by two functions. So, okay, that was just a repeat of the introduction of this fun ring. So, no, it's not. First of all, it's not graded. That would be a filtration. Like any ring of polynomials, there's a million filtrations. You can take the order of vanishing at t equals 17 is also a filtration. They're not particularly interesting for us, and I just want to say what I want to say. The only thing that we will care about is that they vanish at 0. We won't have any functions which vanish to higher order. What we will have, and you'll see it very soon, is functions that vanish to a high order at infinity, or that have a pole of a certain order at 1. So what we do care about, since they're all rational functions, they have orders everywhere, 0 is the least interesting. All of my series will order exactly 2 because they start at d equals 2 or at d equals 1, but it's kind of trivial. There's no d equals 0. But what's interesting is what happens when t is near 1 or near infinity. But we'll see that very shortly. So far it's just an abstract definition, and you can't imagine a stupider definition. I haven't motivated at all. I just say, let me take those two functions, and I like them. But the reason I like them is because you have these theorems that I just erased, that the graph numbers, the Hurwitz numbers, and also several others in the paper. I'll put my co-authors' names again, just in this paper with, I put it out of order because Dubrovin is not only more senior, but he's alphabetically earlier. So put him here, and of course myself, I'm lowest in every sense. So we're writing a paper that in particular gives these elementary computations for Hurwitz numbers, but also relates it. And there are several other problems. Ribbon graph counting and certain Hodge integrals also are shown to give elements in the Lambert space, but I won't talk about that. So okay, now I want to do the graphs. So the theorem, I don't remember the numbering, but I think it was theorem 2. Because theorem 1 was that if d is fixed, then you get a sum of exponentials for the graphs. And theorem 3, I think, was about the Lambert space, that lambda is a ring. I'm not quite sure what numbering I took. And theorem 2 was that if you fix g, then the function d goes to, well, except there's a denominator. So if you take this counting number, then this is in lambda if g is at least 2. And if g is slightly bigger than 2, then it's, slightly less than 2. It can't be much less. If it's 0 or 1, then you get 2 slightly bigger numbers. So I'll actually give you the corresponding, I knew that would happen if I bent this, all the pages fall out. But then it gives me the freedom to take them out if they're going to fall out anyway. It's much more convenient. Okay, so if I define the generating function, but now we know, so I want these functions as they stand. But if, under my isomorphism, which I raised, it should be f of d over d factorial. That's why the actual function, this thing has a denominator. If you multiply it by d factorial, it still has a denominator. It's not an integer, but the denominator is now bounded. So for instance, at most 360 of g is 3. So if you fix g, this is a nearly integer valued sequence. But without the d factorial, it's got a huge denominator, essentially d factorial. So then I can give you the actual values. G0 is exactly t minus t squared over 2, which is exactly alpha minus 2. So it's in the slightly extended Lambert space. It's not a combination of alpha n with n positive. And similarly, G1, sorry, I can't hear you. Thank you. This is a pure typo, or would be a typo if I were typing. It's a choco. A brand new word, a choco. I'm all chalked up with emotion. Okay, and let me give one more. So one more. So the next one will be 3t plus 2t squared over 24 times 1 minus t squared. And so in general, let me define also, and I'll use the same with the Hurwitz numbers and everything else. When I put n in parentheses, that's kind of a standard notation for the nth derivative, but now I mean the nth g derivative. Okay, so I should have called so for this point of view, alpha n bar would be alpha bar n, but I'll never do that. It's too horrible. But anyway, I'll use the n to mean that. So you see that this is only in the extended space. So if I write this in terms of, sorry, this wasn't quite right. Should have been bar. It means that d factorial g0d is equal to alpha minus 2 of d, which of course in this case is given by a closed formula. It's d to the d minus 2. Similarly, d factorial times g1d is a half beta minus 1 of d, which is beta of d over 2d, and beta of d is the thing that's still written there. And similarly, I'll do one more. I'm just the ones that are here. D factorial g2d is, I think I wrote this last time, 5d over 24, alpha of d. So if you want, that would be alpha 1 of d minus 1 over 12 beta of d. So here the polynomials are 5d over 24 and 1/12. Where? Yes, thank you. Ah, boy, it's nice to have good students. Okay. Yeah, nobody else noticed, or else everybody else was too polite. Thank you. What? Okay. Thanks a lot. Yeah, nothing I write is to be taken completely seriously, and nothing I say either. Okay, so here are the first couple, and then if you prefer that, then you can also write this. So in a corollary of this is that you have to think a little bit, it's not quite the same base, but every GG, comma star, is a linear combination with polynomial coefficients of the zeros and the first. I mean, here that would be true with the d factorials, but the d factorial is a common factor. You can remove it. So I'll just rewrite the last thing explicitly for G2. I think I said it last time. Maybe I didn't. So just, if you like, everything in terms of either trees or unicycle graphs, then it would be G2d is 5d cubed over 24 G0d minus d over 6 G1d. And similarly, G3d, G4d, they're always polynomial coefficients of those two. So I want to sketch the proof of this, and then I'll go on to the Hurwitz numbers, and I probably won't finish with Hurwitz today, but that's okay. We have many days, and I'll just continue. I'm going to remove everything because we don't actually care about any of these explicit formulas for anything. The important thing is to have a feeling that this ring is a very simple ring corresponding after the change of variables to just polynomials in 1 over 1 minus t. Yeah, well, I'm going to give that. You're trying to guess the proof, but I haven't yet given the proof. So I've just stated the theorem. But yeah, that's going to be exactly how the proof goes. So give me a couple of minutes. So, okay, so I would like to give proofs. And since I'm feeling, again, euphoric and generous, I'll give you a proof 1, and then a proof 2, and then a proof 3 in less detail, because all three methods, all are kind of well known, but from different points of view. They give a different feeling. They also give slightly different information. And also, I realized that I forgot to say part of the theorem. I believe people said they could actually read what's on the left board. So I'll use it. I'll try to write a little larger in case you're far away on the right. So the final statement, what I wrote or I said in words is that all g, except for the first two, are polynomials in 1 over 1 minus t. But in fact, this statement is stronger. If you write it as a polynomial in 1 over 1 minus t, then, and now I can't remember that I called it kappa, lambda, or mu. I don't want to change notations more than I need to. It's in my notes 6 times, and I don't know. I think it was lambda. Here, lambda. Okay, so let's call these coefficients lambda gi. So just say it's a polynomial. But actually, the most important thing about a polynomial is the degree, of course. But a little bit equally important is the lowest term. So that's about your question. The vanishing at t equals 0 is of no interest. All of these series vanish exactly twice, because whatever you do, once, for Hurwitz numbers twice, because you have there are graphs with just one vertex, so you have d equals 1. But what's interesting is what happens when t is near 1. So as t goes to 1, the biggest singularity corresponds to the degree, but also as t goes to infinity. And at infinity, the biggest singularity is the lowest term, and it's not 1 or 0. It's not an arbitrary polynomial. As a polynomial in 1 over 1 minus t, it's divisible by the g minus first power of the variable. Sorry? Thank you. It's gg, and I won't write the variable. It's gg of z, which, however, remember that we had not just an isomorphism, but an equality. Q of z is the same as Q of t, because any power series in t is a power series in z, and vice versa. So under this association, and of course, this contains rational functions in 1 over 1 minus t. They have an expansion, and by what we already know, we land in that very small subring. Okay, and the rest of the theorem, which I didn't say, gives the top and the bottom ones. So the bottom one I'll check that I got the normalization right, but it's G over G minus BG. That's the G Bernoulli number. I think everybody's seen Bernoulli numbers, and if you haven't, it makes no difference for this except that they're famous numbers. So this is a known rational number. And the top one is more interesting. Well, it turns out that I'll just call it B, except it turns out a little more convenient for some purposes, for others not, to index it shifting by 1, where, and then I'm going to give you several definitions of these BRs, but I'll start with the one that I, sorry? I can't hear you. Thank you very much. Yeah, this is the bottom, that's the top. Thank you. Gee, I'm making a lot of chocos today. But anyway, somebody will alert me to every mistake that I make. So the BR, I'll give several other definitions later in the course of the proof, but the one that I certainly like the most is the log of a divergent power series, which is the sum m from 0 to infinity, 6m factorial divided by 3m factorial times 2m factorial times x, and then there's a normalizing factor, which for me is 288 to the m. So this is a formal power series. It diverges for every complex value of x except 0, but it's a well-defined power series. It begins with 1, so you can take the log, and then you get a new power series beginning with x, and whose coefficients are all rational numbers. Sorry? It's not the area function. Please, please ask questions only about what I've done. Lots of people here are experts, and people keep guessing. This is, however, not the area function, but it does describe, if you take 1 over x, the asymptotics of the area function at infinity. It's not the classical area function, which is given by a different thing. But it is, of course, in some version of the area function, and it has many other meanings. So it's familiar to many people here. But I want to give my surprises at my own speed. Sorry, no, it's okay. Just never do it again. Okay. Well, for 5 minutes. Okay. My bark is definitely worse than my bite. Okay, so I have a killer bark, but I don't have a killer bite. Okay, nobody got that one, maybe they did. Okay, proof 1. So proof 1, somebody already sort of said how it would go. This one is by what I hate. This is the method of hate I really dislike. I don't like pure, and I definitely don't like thought. So this is a pure thought proof, but some people like that, and these two are the way you're supposed to do mathematics that God intended, which is by pure calculation, by brute force. So those are the nice proofs, but I'll give the ugly proof by pure thought first, which is actually, I'm sure all of this is extremely well known. I don't claim for anything here any originality except maybe the combination of the order of putting things and this emphasizing the Lambert ring. So let's start with g equals 0. So what is G0D? Well, this is the number of trees, the number in the usual sense, wonderful automorphisms, of trees. A tree is a connected and simply connected graph. So 0 cycles, G is 0. So on D vertices. Now this was already computed in the 19th century by Cayley, and the result that I said, this alpha D, is Cayley's result, but I'll give you a complete proof because it takes 2 minutes. And this meant to be a graduate course. It's very beautiful, very simple. But it turns out, and actually this you'll see several times, certainly with the Hurwitz numbers, and also I think in the other series of lectures here, often it helps to differentiate at least once, which means here multiplying. So G1D, sorry, that's not what I mean at all. I mean G1D, which is simply DG0. So this would correspond to the generating series G0, and this would correspond to the generating series G01, which remember meant DG0. So if I just multiply by D, this is the number in the usual sense, sum 1 over the number of automorphisms, of rooted trees. So a rooted tree is a marked tree, but because actual trees, when they're marked, that's called the root, so we call them rooted trees on D vertices. Okay, so let's take an example. If D is 3, then the only tree that you have is this one. And so G03 would be a half, because this is the only tree and it is one automorphism. But on the other hand, if you have a rooted tree, there are two ways to take the root. You could either take an endpoint, or you could take the middle point. Or you could take the other endpoint, but of course that's the same tree. Now this one has no automorphisms. But this one, you can still flip these two. So I get 1 plus a half, which is indeed 3 times 1/2. And it always works because you have d ways to pick the root. And after you pick it, you have to worry about how many symmetries preserve that root. But the beauty of counting things with wonderful automorphisms, it takes care of itself. I'm not going to explain that. It's a thing you have to think about 5 minutes till you see why it works. But in any situation like this, you can just say completely naively, as if you didn't realize that there could be a subtlety, a tree on d vertices has d vertices. To pick one to call it the root, there are d ways. You just multiply by d. And although that changes the automorphism locally, when you sum it all up, it comes out right because we're counting exactly with the stabilizer. I don't want to go through that. It's a standard thing that is best not explained, but just thought out for oneself. So now, therefore, the corresponding generating function, g1 of z, let's call it t. It's going to be our t, but we don't know that yet. So let's call that g1 of z. Sorry, g0, 1 of z. So it's the generating function of rooted trees. So we could work out the first couple of numbers, and of course it would be what you think. But now let's look at this. All rooted trees, well, any rooted tree has a root. It can't be empty. It's got the root. And that root has a valency. The valency of a vertex is the number of incoming edges. Let's call it k. Of course, it might be 0. Only if it's the tree of 1 point, which is a rooted tree with 1 point. So if I take all trees and I fix the valency with root of valency some fixed number k, well, then I have k things coming out. And each of those is an edge, and it has 2 endpoints, one of which is the root, but the other is a new point. And now you see that if you remove the root from the tree decomposes into a union of k disjoint non-empty trees, and what's more, they're rooted, because from each further edge, you have, it can be arbitrarily complicated, but it's still a tree because it's simply connected, and it's got a root, which is the point that was originally connected to the main root. So therefore, you see that the set of all trees, so I just put generating function, the generating function of all rooted trees with valency of the root k, well, you simply take t of z, that's the generating function for the first tree, and then you take to the kth power because we have k trees. Of course, you can put automorphisms on each one, but they're included in the definition. And then you can permute the k. So you divide by k factorial. Again, everything works out fine. But then you've forgotten 1 point. I've counted every point after I moved the root. So it's z times that. That's it. That's the generating function for things with valency k. And therefore, since every tree has some valency which may be 0, you immediately get this. And so z is our famous t e to the minus t, and t is the thing that it's meant to be. And the Lagrange theorem indeed tells you, the Lagrange inversion theorem, that the number of points is d to the d minus 1, as it should be. And so the number of rooted trees is d to the d minus 1, and the number of unrooted trees is d to the d minus 2, which is exactly what I said. So that's, I don't know if that's Cayley's argument or not. There are also bijective arguments. Anyway, I don't care. This is the argument I want to give. So that takes care of the case g equals 0 by hand. So I'm going to follow the other speaker and do so many cases by hand that then you feel happy that we can do the higher ones not by hand. I won't give as many terms as he did, but I want to do also the next case, g equals 1. So we've shown that for g equals 0, I'll repeat what we just did, take the generating function for rooted trees, differentiate it for all trees, differentiate once to put a degree. This is exactly our t in q of t. Of course, it's not a polynomial in 1 over 1 minus t. That's why it's slightly extended. Remember, this one was alpha minus 1 or something. OK, now I do g equals 1. Now, g equals 1 means that you have a graph which has 1 cycle. But if there's 1 cycle, there's a unique cycle with no backtracking. There's just 1 path where you go around and never come back. Because the only other thing you could do is go up one of these trees, but then you'd have to come back. So without backtracking, this unique cycle. But you have to start somewhere, and you have to pick a direction. So actually, the number of automorphisms in a set will be 2k, where k now has to be at least 1 is the number of vertices on the unique cycle. I'll just say the cycle. So gamma, here I'm picking gamma, is a graph, connected graph, with one cycle, so unicycle, people seem to call it. Then there's one shortest cycle, the unique one with no backtracking, and it has a certain number of vertices which cannot be 0. It has to be at least 1. So call it 1. Then, if I number them, so I pick 1 and I pick a direction, then I've numbered them all. So that's like the comment yesterday about the ribbon graphs. In this case, you just need an orientation and 1 point. So there are 2k ways to choose a number. You pick an origin, you pick a direction. So that's 2k, which I'll have to divide by. And now you see that the complement of this cycle is a bunch of trees, but those trees include this vertex. So here you get simply t to the k, and there aren't any z times t to the k. There's no extra point. So you just have k trees, and you have to divide. And therefore, the generating function that we're talking about is the sum k from 1 to infinity, t to the k over 2k, just by pure thought. And this is, of course, 1/2 log of 1 over 1 minus t, which is exactly what I said it was. And therefore, its derivative, as I already also had said before, when I talked about the derivative, that would be 1/2 times t over 1 minus t squared. So it is a polynomial once you differentiate once or twice. And similarly, g0, if you differentiate twice, becomes a true polynomial in 1 over 1 minus t. So they're all in the Lambert ring except g0 and g1, which are in the extended Lambert ring. But even those, if you differentiate once or twice, are in the Lambert ring. So morally, they all are. So now we've done genus 0 and we've done genus 1. But now let me do general genus. And the fun thing is it works by itself. So let me write gr is all graphs. Now I want to get my notations right. I guess gr g gd. Where do I have my notations? I don't see where I put the notation. So graphs, all graphs, connected graphs. And gr greater than or equal to 3 means greater than or equal to 3 valent graphs. So I allow vertices that are trivalent or 4-valent or higher, but I don't allow kind of stupid vertices where you've just added a random vertex on an edge, and I don't allow vertices that float in space, so 1-valent vertices. So we have a map from here to here, and it will preserve the number of cycles, and it's simply the following. If you have a graph, if it already is no 1-valent and 2-valent, you're done. You just take it. But if there's a 1-valent thing somewhere, you just pull it. So here's the rest of the graph. You just shrink that to a point. You just remove that edge. So it's like a snail withdrawing its tentacles or its feelers. And so you just pull that in, and then you pull in the next one. Well, if you think about it, the order doesn't matter. You're just shrinking every tree to a point. Now, when you've done that, there won't be any 1-valent vertices left, because you would keep shrinking. But there may be some 2-valent vertices, but they're so stupid. There may not have been any originally. Your thing might have had no 2-valent vertices and looked like this. But once you shrink this to a point, and then you shrink that to a point, and then you shrink that, you'll be left with a useless, unmotivated vertex, and nobody wants this. You just throw it away, just discard it. So that gives a map, obviously surjective, from here to here. Now, if I take some graph gamma here, what are the gamma prime that go to it? Well, here's my graph, which is now at least 3-valent, but it has some edges. So here's my graph gamma, which is E of gamma edges and V of gamma vertices. Well, at every vertex, originally it's at least 3-valent, but I'm allowed to add a tree any way I want. Okay? Including the tree consisting of just that point. And so that's all I can do at that vertex. That vertex was obtained by shrinking a tree together. It might have been a tree of just one vertex. So there's an associated, in anything in the pre-image, there's a rooted tree of which that's the root. So if I go to everything that it contributes, then I see that the contribution of this vertex will be T of Z times what it was originally. Well, or just that. So since there are V of gamma vertices, I'll get that. Now, how about on an edge? On an edge, there may have been lots of previous trees with which I shrunk them to a point, gave a 2-valent vertex. That means that after I'd shrunk all my trees to a point, on a given edge, which I now imagine oriented, because the automorphic suppressions have been taken care of, so I've Anyway, they're oriented, you can't permute them. They're in a straight order. You only have to write the orientation. Call them 1, 2, 3 up to k. But of course, k might be 0. There might not be any. But after you did your shrinking, you might have had an edge with no 2 valent vertices. But you might have had k of them. So let's put in k, and then in each one, we can assert an arbitrary tree. And so I'll get t of z, I'll just call it t. It's the counting function of trees. But we now know it is the same t. It's the Lambert function. It's the inverse function of z equals t e to the minus t. So then I'll get t to the k. That's the contribution from any edge which has exactly k vertices on it. But since k can be anything from 0 to infinity, I get this sum, which is 1 over 1 minus t. And so every edge will contribute I'll just call it t. So if I have this graph gamma, and I ask, what is the contribution of the generating function of all trees, trivalent or not, with no constraints on valencies, the answer is very, very simple. The contribution of the graph is this, but of course it's only correct because, as usual, I count with 1 over the number of automorphs of the graph. And I've put the other automorphism here in the definition of t of z already. And so I have to sum this over all graphs with a given number of cycles, and they're at least 3 valent. Nuisance. Okay, so that's the formula. Well, now we're kind of done. So this is g of z. And you see, script g. You see, I'm already done. This is, the only thing I have to check is that this set is finite. And that's a very simple argument. So let my graph gamma, which is at least trivalent, so if my graph gamma is greater than or equal to 3 valent, so does ni vertices of valency I. But of course, I is greater than or equal to 3. Okay, then the number of, let's say it is n points and k edges. Then n is obviously the total number of vertices, and every vertex has some valency. But 2k is the number of half edges. Every edge has two half edges, and every vertex, which is trivalent, has 3 half edges. Every 4-valent one has 4, and so on. But because it's connected, we also know that this is 2n plus 2g minus 2. So therefore, 2g minus 2, I have to subtract twice this from this. So it's n3 plus 2n4 plus 3n5, and so on. That obviously bounds n3. If g is, remember my g is no longer 0, 1. I did those by hand. So this is some positive number that bounds n3, it bounds n4, it bounds n5. But it also bounds the number of ni's. Because if you had an n100, even if it were 1, it would have a coefficient 99. That would be too big. So each I is bounded, and the ni is also bounded, so the whole collection is bounded. So it's a finite collection of graphs. So the advantage is the original set of graphs was, of course, infinite. We had a power series. But this thing is a finite sum. And so this is a finite sum. And that certainly shows the main part of the statement, which is that it's in the Lambert ring. This is certainly, and also V is, remember that this one is n, and this is k, which is n plus g minus 1, I think. So it's certainly bigger. So therefore, this thing is small at infinity. So it's a polynomial in 1 over 1 minus t. Now, the only thing that's left to prove is that the degree. Well, you can also see from this that the biggest thing that you can have, the biggest possible denominator, E of gamma is n plus g minus 1. G minus 1 never changes, but n, which is n3 plus n4 plus n5, is less than or equal to n3 plus 2n4 plus 3n3, which is 2g minus 2, with equality if and only if n3 is 2g minus 2 and all the others are 0. Right? Because otherwise it's bigger. So the highest term, the most singular term here, is when n is 2g minus 2. But then n plus g minus 1 is 3g minus 3. And how many are there? Well, that's just the number of trivalent graphs. So now I claim that this BG, the real definition of this, it's the number of the number in the usual sense, 1 over automorphisms, of trivalent graphs with first Betti number g. That's really the definition. That's what I've already showed. Now let me show you this explicit formula. But if I just said bg minus 1 is the number of, so this b1 is not that b1, this is the first Betti number. Well, you know what I mean, g cycles. But now if I have a trivalent graph by the calculation I just gave you, then we have to have n and k. And by what I just told you, since it's only an n3, n is equal to n3, and k, which is n plus g minus 1, is 3/2 n3. So therefore, n3 better be an even number, call it 2m. Then this is 3m. And then you see that the difference of these, which is g minus 1, is m. So g is therefore m plus 1. So that's why I'm actually calling it b sub, well, I should have called it r, excuse me. Yeah. Where? I may have, probably I did, yeah. Now I don't remember anymore, but I can check. I mean, I have it right. Let's not worry about it, it's just an example. Why don't I just cross it out? It's, well, I mean, I can look, it's silly. It should be 3g minus 3, and if g is 2, 3g minus 3 is 3. Yeah, that was a typo, thank you. The chalk is not behaving well today. Three types? I have no idea what you're talking about. I think let's discuss after. I don't want to start a discussion of things I don't understand. I have no idea what you mean by three types. I think what I said was the correct proof, and there's only one type. You shrink one valent vertices, you remove two valent vertices, and you get this map, and you get exact. I think this is correct, but if it isn't, please tell me afterwards. I want to know, but I don't want to be told now, because if I said something wrong, I can't think about it. Okay, so here, if I call this number r, then trivalent graphs on r vertices which are connected are this. But now it's the usual argument that we know that BR, if BR is defined that way, as trivalent graphs with this number, you know, 2r vertices and therefore 3r edges, but connected, then we know that the corresponding generating functions, so BR, I define by trivalent graphs. Then by definition, it's the log of the number of all trivalent graphs, not necessarily connected. But that is almost an exercise to see that this is the number of all. So this is connected. And then this thing is the same with all trivalent graphs, possibly disconnected. And I mean, there are many ways to see this, but one way to do it is you say we have 2m now vertices. So each vertex, you have 2m things like this. And I have 3m things that look like this. Okay? And I number everything in sight. So this is called A, B, C. And then A1, B1, C1, because this is the first vertex up to 2m. And similarly, I have 3m of these, and they have a left endpoint and a right endpoint. Now, when I do that, to make my graph, which is now completely arbitrary, I just have to decide that this half edge is that half edge. I mean, here, I shouldn't have made those points. Each trivalent vertex is 3 half edges. And similarly, this one has 2 half edges, the edge. And each half edge at an edge has to be a half edge of a point. And it's completely arbitrary. So how many ways? You have 6m half edges here, and 6m half edges here. How many bijections are there between two sets of 6m elements? Well, it's 6m factorial. That would be if I labeled absolutely everything. I've labeled the 2m vertices, I've labeled the 3m edges, and I've labeled each of the 3 endpoints, incoming half edges at each trivalent vertex and each endpoint of the edge. I've labeled everything. Now I have to divide by the number of ways of relabeling. Well, I have 2m points, I numbered them, so I should divide by 2m factorial. But I also had 3 points, and so there are 3 factorial ways to order them. And I've done that for every one of the 2m. Here I had 3m edges, and I numbered them, so there would be 3m permutations. And then I have 2 ways, 2 factorial if you want, to the 3m. And so the rest of the proofs that 3 factorial squared times 2 cubed is 288, which is an exercise. And so you see it's exactly the formula I gave you. I don't want to say more about it. If that was clear, I'm happy. If it wasn't, think about it till it becomes clear. It's a very simple argument, and it has nothing to do with the rest of my talk. These numbers come in many places in mathematics. One place was mentioned by various people. It's the asymptotics of the area function at infinity. It's not convergent, but it can be the asymptotics of a function. And another place is in a paper, a formula that is in a paper that isn't written and never will get written by Fabre and myself, but he's lectured about it in many places, so the formula is now known. And it's a formula that describes the lowest degree tautological relation in the cohomology group or the Chow ring of the moduli space of curves. And that smallest relation involves certain numbers, and it's completely determined by certain numbers. And they are exactly these BR. They start 5 over 24, 5 over 16, I think. I'll check in a second. 1105 over 1152. Anyway, these numbers came up there. They also are trivalent graphs. They come up in several places. They also satisfy various recursions, which I may or may not still come to. It doesn't matter. I mean, I just mentioned that these same numbers occur in some work I did that is unpublished but quite well known on the tautological relation in some moduli space of curves. It's not part of these lectures. I just mentioned it. Yeah, the space of curves, MG, the moduli space of curves, has a ring, and it has what's called the tautological subring. There's some famous classes called the kappas. And they're kappa 1, kappa 2, and they have relations because it's a finite thing. And the lowest degree relation is in dimension roughly g over 3, and we found it, and it involves these numbers. I don't want to go into details. It's not my subject. I just wanted to mention that these are fun numbers. I'd be happy to tell you privately. I mean, I love these numbers, just they're not part of, it's also much more advanced than the level of this course at the moment. Okay, so that was proof 1. Now, proof 2. No, that's a good question. You can interpret it. I just removed the formula, but the bottom thing would be the lowest value, and then you get a sum over all graphs of something, and so you get a corollary that that number is a Bernoulli number, but I don't know how to get it from proof 1. So I said that's one reason for more than one proof. They don't all give everything. I don't actually know. And for the Hurwitz, it's even worse. The lowest coefficient is again a Bernoulli number, and that actually gives some new Hodge integral calculation that seems not to be very interesting, but that we don't know a priori. So I don't actually know why the mathematical god took all the trouble to make this such a nice number, Bernoulli numbers, because I have absolutely no interpretation. That's a good question for you people. If one has an element in the Lambert ring, so if it's a sequence of rational numbers, f of d, that maybe are counting, graphs, coverings, or something interesting, then you can ask, well, the generating function, the f bar, will be a polynomial that will have the biggest degree, let's say capital D, and the smallest degree, let's say little d, with corresponding coefficients, little c. The biggest degree is no problem. That determines the asymptotics. I'll talk about that later. That determines the growth. Everyone wants to know about the growth. But I have absolutely no idea what little d means, let alone c. So what it means that this polynomial only vanishes to a certain order of infinity in terms of the numbers themselves, what property does it reflect? I have no idea. And if somebody can tell me, let alone what the coefficient is, but even the degree. So I don't even know what it means that this polynomial, the first g minus 1 coefficients vanish. And c g minus 1 is the first non-zero one, let alone that it's a Bernoulli number. That would be so that's a good question. I wish I knew the answer. We have no interpretation. So now I'm even more. I thought I would spend 10 or 15 minutes doing the 3 proofs and go on to Hurwitz. And now I've used up the whole hour, and I've only done one of the 3 proofs. But I think that's no excuse for anything. We have to make a pause anyway. So let's say 10-minute pause till 9 minutes past 3. OK, so proofs 2 and 3 also use familiar ideas. Proof, actually, because of a conversation I just had, I'm changing the order, but what's going to be proof 3 is now 2. So proof 2 uses a very well-known idea, and proof 3, I'll only give a sketch. It's no more complicated than the others, but it's almost the same as the only reason with the proof that I will give for the Hurwitz numbers. And so I'll just sketch it so that you see that they're parallel, and then I'll give the details in the other case because they're very similar. So for proof 2, we're going to go back to the fact that, where's the well-written copy of this? So remember that we have the generating function of all connected graphs. So here I'm going to put Now I can't remember. So it's x to the number of edges, y to the number of vertices, divided by the usual automorphism of gamma. So in terms of my notations, that's GGD times x to the number of edges, which remember was d plus g minus 1, y to the d. And so since I'm writing, remember, script GG was the generating function if you fix the genus. So here, I can think of this as a single one-variable generating function, in G, with a single variable, x to the g minus 1, but in front I put GG of z, which is now going to be xy. But you notice, and this will play a role in a second, that d, which was z, d by dz, is also the same as y, d by dy, right? Because z and, if you think of x as fixed, then z and y are proportional, and so z, d by dz is the same. So when I talk about d, it doesn't matter whether I think of it in terms of y or in terms of g, right? Because you still multiply by d. Okay, so that's what we have. And we know that what I called yesterday zg, which was the partition function, so this is the enumerative function, this is the partition function, is the sum over all gamma of the same thing. And then by the same principle, which I used yesterday and also used again today, that was the exponential of the connected ones. But this one, there was a simple counting argument, which I'd already given, which said that, so this is by definition the same thing, but now it's x to the k, y to the d, and k is the number of edges, d is the number of vertices, and then the coefficient here was the number of all graphs, and there was a very simple argument that showed that that was equal to, now I don't remember, 2 to the k, k factorial, d factorial, times d to the power 2k. And so if you sum that over d, over k rather, what it gave you was a power series in y, but the coefficients were actually polynomials in e to the d over 2, and that's how we got the behavior, the description of how it looked for a fixed d, because if you take the fifth coefficient, it will still therefore be a polynomial in e to the d over 2. So that's what we had already used. And so now both of the other proofs will use that expression, so both of them will depend on the passage from non-connected, or from connected to all graphs, and the fact that for all graphs the formula is completely easy in this case. It's not for the Hurwitz numbers, but in this case the corresponding question is trivial. The formula is given in closed form by this, what I just wrote, d to the 2k over 2k k factorial d factorial. And so you have this formula. Thank you. More chalkos. The chalk is really not in good shape today. We should complain and ask for better chalk that doesn't make mistakes. Okay. I keep wishing they would invent it. Okay, so this is the formula I want to do, and I don't know whether to use, I typed it this morning, but the printer is so small that it'll ruin my eyes. I don't want to get the formulas wrong. So now I use the method of Gaussian integrals, which several of you, or now it's called Feynman integrals, but Gauss came before Feynman, and he invented the method perfectly happily without any help from Feynman. Okay, so e to the power n squared x over 2 is equal to 1 over the square root of 2 pi x times the integral minus infinity to infinity e to the power nu minus u squared over 2x. Okay, I think that's a very familiar integral. The integral here, you make a shift in u to kill the linear term, just like you learn in school when you solve quadratic equations, and then that pulls out a quadratic factor, an exponential factor, which is e to the n squared x over 2, and what's left is just e to the u squared over 2x, which is a constant over times square root of x and the constant square root of 2 pi by computation done by Gauss. Okay, so we have this identity, and therefore my zg of xy, but remember I don't want y to be y, I want to work with z. So z was xy, so therefore y is z over x. So now I take this integral, or maybe I'll just write it again, because I've already forgotten where it's gone. First of all, it was d equals 0. here, because non-connected, and it should really be n. It should be n, sorry. The d was a mistake. D is always at least 1, but this n is, of course, it doesn't make any difference, but you should always use different letters for different things. Okay, so y to the n over n factorial e to the n squared x over 2. Now I insert this integral. And I see that here, this part is minus u squared over 2x. But the first part is the sum e to the nu times y to the n over n factorial, but that's simply the exponent of y e to the u. Except that y is not y, it's z, and that's very convenient because that's exactly y it's z over x. So I have this x down there. Okay, now we use stationary phase. So here you have some integral, you have some function you're exponentiating, so if the function is a maximum, the exponential of it is a maximum, and everywhere else it's much smaller. That's not quite a rigorous argument if we don't know, real and so on. Everything here is real, and it's a formal calculation anyway. It's completely okay. So we have to use this method called stationary phase, which also goes back to Gauss, basically, and certainly to people in the 19th century doing things like Hamiltonian mechanics and least action and so on, which of course later led to similar action principles in quantum mechanics and quantum field theory. So you use this method of stationary phase. We won't look at the maximum. And so the maximum is of course obtained when the derivative of the exponent is 0. The derivative of the exponent is 1 over x times z e to the u minus u. Right? If I just differentiate z e to the u minus u squared over 2. And so this should be 0. And so you see that that means z is equal to u e to the minus u, which means u is our famous t. So we already see that the maximum of the thing is attained at the very same t that we've been talking about all the time. And so if I expand around that, I just make a shift. Then I'll call this t plus v minus t plus v squared over 2 dv. Okay, so I've just set u equal to t plus v. I've just shifted my real line. Now, I want to know what this looks like. Now the interesting point is 0. I've now moved the singular point to v equals 0. When v equals 0, then the leading term here starts z. Wait a second. When v equals 0, I have z e to the t. But remember, z is t e to the minus t, so that's just t. And then here, if v is 0, I have t squared over 2. So the first term will be t minus t squared over 2 divided by x. And unfortunately, I erased the theorem of which this is the second proof. But the theorem said that in particular, remember that we want the log of zg of x and z over x. The log of this, we know, that's what's written on the right board, is the sum of the generating function that we're looking for, gg of z, times x to the g minus 1. So in particular, we already know that in terms of z and x, rather than x and y, the log only will have a simple pole in x, and the coefficient will be g0. And the first statement of the theorem was that g0 of z is t minus t squared over 2. So that should come with the 1 over x, and here it is. That's just the value of this thing at v equals 0. And now what I'm left with is 1 over the square root of 2 pi x. And here I have to take, no, I haven't yet made a mistake. I'm sure going to happen very soon. Yeah, it's already happened. It's minus 1 minus t over 2x times v squared plus the sum r from 3 to infinity t v to the r over r to the r factorial times x dv. So please check if I did that correctly. So I've simply taken this exponential. I've exponentiated every term. So the constant term was, as we saw, z e to the t is t minus t squared over 2. The linear term drops out because we made it drop out. right? The derivative vanished. So the derivative would be z e to the t, which is t minus t. It's 0. The quadratic term would have a term z e to the t, which is again t, times v squared over 2. So that's this plus t v squared over 2 divided by x, minus this v squared over 2, so that's that minus 1 over 2x. But all the other terms come to the exponential, and it's just z e to the t, which again is t, that's this t, times v to the r over r factorial, and then the same x. So here r equals 3 is there, r equals 2. That part would contribute this part, but there's the extra bit from here. The linear term went away, and the constant term I took out. Okay, so far we're this far. And now I want to rescale, of course, because v is very small, but x is also very small. So let me write it at the top of the board. So this becomes x of t minus t squared over 2 divided by x. If you're taking notes, don't close the parentheses yet. And now I want to make a rescaling so that my Gaussian becomes a standard Gaussian. So the standard Gaussian is going to be e to the minus w squared over 2. And so I'm going to make the change of variables that v will be w times the square root of x over 1 minus t. These are just constants, that there are some formal thing I don't really care. So I rescale v to be w times the square root of x over 1 minus t. If you have to think of numbers, think of x as positive and t as small, then I'm taking the positive square root of x over 1 minus t. It's completely irrelevant. So if I make that rescaling, the first term, v squared, gets a factor x over 1 minus t that kills this 1 minus t over 2, and it gives me exactly e to the minus w squared over 2. However, dv also picks up a factor. When I do this to v dv, I get a square root of x divided by the square root of 1 minus t. The square root of x kills this square root of 2 pi, but I'm left with the square root of 1 over 1 minus t, which I can write as the exponential of log 1 over 1 minus t. And I still have the square root of 2 pi, because we had a 2 pi x. But now the x went away. The square root of x canceled. This square root of x canceled. That square root of x. This square root of 1 minus t is a factor, but I want to take the log, so I call it x with half the log. And so that was the next bit of the theorem, which said that the next term in the asymptotic expansion was meant to be, it was written, but I erased it, so I have to write it again. The next term was half log 1 over 1 minus t, and that's the typical term that comes from the determinant factor in the Gaussian. So now we're left with this, and now I have to exponentiate everything that you see here. The e to the minus w squared I took out. So let's do it, but I'll exponentiate in my head, because I have this very powerful head. I can do that. And so I'm only going to do 2 terms. That's as powerful as my head will work. So this term was just e to the minus w squared over 2. I took it out as a factor. The next term is t times v cubed over 6x. But since v is w times a power, that's w cubed, and the power is x to the 1/2. So that will give me a square root of x, 3/2 minus 1. The 6 will survive, the t will survive, but the v also had a square root of 1 minus t. So the next term, when I exponentiate that thing, it starts with this very same thing. But then the next term, I'm exponentiating. That term is in the exponent. So here, there are some funny square roots that I wouldn't want for my Lambert ring, but luckily, w cubed is odd. And when you integrate against a Gaussian, any odd polynomial will, of course, drop out. So that won't cause any trouble. But when I exponentiate this term, the next term will be 1 over 2 factorial, which is a half, times its square. So it'll be t squared w to the 6th over 2 times 36 is 72 times 1 minus t cubed times x. But I'm not finished, because that's just exponentiating the square root of our term. That came from r equals 3. But the next term would be r equals 4. And the r equals 4 term would be t v to the 4th over 24x, because 4 factorial x. But v is w, but times the square root of x. Square root of x to the 4th is x squared. Divided by x is 1x. The t remains. And this time, the 1 minus t to the 1/2 to the 4th power is an integral power. So I'm in good shape. So here it's plus t w to the 4th over 24 times 1 minus t squared, etc. And it's completely clear that you can expand this to any degree, and the exponent will be a power series in X whose coefficients are polynomials in W or W squared, and polynomials in 1 over 1 minus t, or sometimes the square root, but the parity is the same, so square roots will only occur with odd powers of W, which will drop out. So I'll finish this quickly because this is not what I really want to talk about in this course. It's just to show you the different methods. This is particularly well known. Now remind you of the value of this famous Gaussian, well, divided by square root of 2 pi. This is 0, as I've already said, if n is odd. That's obvious because the integrand is odd, so it drops out. And if n is even, then it's n minus 1 double factorial, where, for instance, 6 double factorial means you start, well, 5 double factorial means 5 times 3 times 1. You go down steps of 2. Many, many years ago, when I was a very young man, I showed this notation to Serre, who, believe it or not, had never seen it. And he was furious. He said, people can't use that notation. Ça ne saurait être autre chose que. He said n factorial factorial can only mean n factorial factorial. And I said, well, in principle, you're right, but the fact is that this will never occur in a billion years, and it's very convenient, and everyone uses it, so I'll use it in my paper. He was for Compte Rendu, and he was the editor. He said, you can't use this. And then a week later, he came back, and he said, you know, that notation is really good. So I'm sure he doesn't remember, and he uses it all the time. Sorry? Well, of course, yeah. I mean, you can't expect, Maple to know things that even Serre didn't know. Okay, but anyway, he knows now, whereas Maple apparently still doesn't. Okay, so now when I do this, then I won't do the whole thing. But this part, well, the integral of 1 is 1. The next integral is 0. But then this integral, I've put 5 double factorial, which is 5 times 3 times 1. That's 15. 15 over 72 is 5 over 24. And then the next term is 4 minus 1 is 3. Double factorial, 3 times 1 is 3 over 24 is 8. The chance that I haven't made a mistake is minuscule. And so you get a power series that starts like this. And now when you take the log of that, you drop the 1 and keep this. And so we have now one more term. So the final answer would be that it starts t squared minus t minus t squared over 2 over x. The next term is a half log 1 minus 1 over 1 minus t. The next term is just what I just wrote. Then there'll be something times x squared. And it's clear from this description that you will only get polynomials in t over 1 minus t from now on out. And that proves the theorem. And you can also see, remember where this term came from. We started with r equals 3, which was t, it should still be written somewhere. It was t w cubed times the square root of x over 1 minus t to the 3 halves times 6. But now when you take powers of that, those powers, it's easy to see for the same reason as with the trivalent graphs. The thing that gives you the biggest contribution, the biggest pole in t, is the pure exponential part of this. But the odd powers of this will always drop out because they're odd. So we take even powers, and so that will be t to the 2m, x to the m over 6 to the 2m, 1 minus t to the 3m, and then we have still a w to the 6m, which when you integrate gives 6m minus 1 double factorial, which is of course the same as 6m factorial over 2 to the 3m times 3m factorial, and then you see 6 squared times 8, just as before you get the same thing. So you will also get the leading coefficient. And I forget, please don't ask me whether you get the bottom coefficient. I can't remember. I think I didn't succeed from this second proof in getting the bottom coefficient. Are there questions? This is the least interesting part in that it's the most interesting part, but it's very well known and it's not what I'm talking about in this course. I just wanted to include it. I want to get to other kinds of combinatorics. So this was just a side remark. It's very familiar to half of the audience, and the other half will see it 100 times in their future life. This is somehow a method, but it's a wonderful method, and one never quite tires of the fact that it actually works, unlike so many methods that just don't. Okay, so at this speed, I'm not going to get to my next topic. I'll be lucky if I finish this topic. So now proof 3, which was actually proof 2. So once again, I'm going to use that e to the g with this z sub g, which we know is the sum n from 0 to infinity, e to the n squared x over 2, y to the n over n factorial. But g, of course, itself, once again, is g of z, x to the g minus 1, and z is xy. So again, we want to use this. And actually, if you think, of course, you remember everything I said yesterday and all formulas. I don't, but you surely do. I used this thing to give 3 different differential equations for G. One of them was kind of the stupid one. You don't even use this formula. You just say, since G is the log of e to the G, which is Z, then you immediately see that d of Z is d of e to the G, which is d of G times e to the G. And now if you plug into this the definition of Z and the definition of d of Z, you get a linear recursion. That was one method. But then we also had that d squared of Z, so this is d, this is not small z, that's, it's the ZG. Another one was that if you applied d squared twice, d is just multiplication by n, so if you get capital D squared over 2, you multiply by n squared over 2, that's the same as if you differentiate in ZG. And this also implied a differential equation for G. And the third way was that we also said you can take ZG, and again I applied DZ, but now I don't use, so this is essentially the heat equation. I don't care that this is n factorial. I only use that whenever I have a y to the n, I have an e to the n squared x over 2. So I don't care that it's n factorial. But for the third equation, I don't care so much that it's that, but I do care that it's n factorial. Because when I differentiate, I get n over n factorial, but n over n factorial is the same as 1 over n minus 1 factorial, so I can shift n, and then the y to the n becomes y to the n plus 1, so I get an extra y. The e to the n squared x over 2 becomes e to the n plus 1 squared x over 2, so that has a factor x over 2, and it has a factor e to the xn, which is simply you replace y by y e to the x, and the rest is unchanged. So we also had this equation, and this gave some kind of a differential differential functional equation for G, just by taking the log, which I'll write out in a second. I already wrote it. We used that. So this gave 3 different kind of differential equations. And from each of them, yesterday, I deduced that for D small, in the expansion for small powers of x rather than of y, then you got polynomials in e to the dx over 2, and we got 3 different recursions for the coefficients of those. Now, these 3 equations are still true everywhere. That's the wonderful thing of differential equations. Once they're true, they're algebraic. If they're true at one singularity, they're true at the other. You can relate the behavior. But I don't know how to use 2 of them. I only know how to use the third one. So the one that I do know how to use, and I hope it's written in a readable way somewhere, so I don't get it mixed up. So I'd written the recursion. This is, I think, not the best value. Damn, it is written up, but here. Okay, so here it is. So if you use this, then what you'll find, so you just take the log of this. So write z to be z to the g, apply this differential equation, but of course it becomes nonlinear. And what you'll find is the following, that if I take the full generating function, g of x, y, and I apply d squared minus d. So d, remember, is either y d by dy or equivalently z d by dz. Think of x as fixed, then it doesn't matter. And then this one will be the product of actually, so why don't I use my notation? D to the n of anything I'm going to write by putting an n. So what I just wrote is easier to write g2 minus g1. If I don't write the argument, it's just xy. But then, if you do this, what you find is that it factors. It's a one-line computation from what I've said. It factors like this. So this is the equation. It's the same one I hope I wrote yesterday, which if you expand around small x, tells you the thing that I just said, that you get polynomials in e to the x over 2. But now we're going to think of it in terms of z. But now we can expand this by Taylor's theorem. So this is g of 1 times the sum L from 1 to infinity. So let's expand this as a Taylor series. Well, think of this as the log. So I'm shifting the log of y by x. But it's the log of y that I differentiate in when I apply d. So the usual Taylor theorem says if you shift something by x, you get the sum nth derivative over n factorial times x to the n. So I should go L from 0 to infinity of x to the L over L factorial times the nth derivative, but the nth derivative of g1 is just gl plus 1. However, it's not from 0 to infinity, it's from 1 to infinity because I'm subtracting the constant term. So it's this product. So that's the identity, that's the recursive function. It's a strange, here it's a functional equation, it's not a differential equation. Here I differentiate, but here I also shift the variable. In terms of log y, I've done a shift by x. But now I've expanded, so now there's no longer a functional equation. The argument now is always the same, it's just z. But to make up for it, it's a mess because I've got an infinite sum. But now if you do it coefficient by coefficient, then what you find, if I just now take the coefficient of whatever it is to the g, x to the g minus 1, then what you'll find is you have the sum L greater than or equal to 1, and then here I'll have some genus g1, and here I'll have some other genus g2, which are each greater than or equal to 1, and the condition that I need in order that I'm talking about the right coefficient on the left, the left coefficient on the right, is g1 plus g2 plus L is g plus 1, and now it will be simply 1 over L factorial times g1, first derivative, and g2, L plus first derivative. I want to, first if you take notes, I want to give you a chance. I want to take half a minute to think about this formula. First, you see where it came from. Every time that I have an L, this I expand, sum over g1. Then I'll have an x to the g1 minus 1. Here I'll have an x to the g2 minus 1. And here I'll have an x to the L. And that all has to add up to the right thing, which now seems to be this is wrong, but it's got to be right, because it is right. So it's g1 plus g2 plus L equals g plus 1. But L is at least 1, because it's the same L. And this is now, therefore, a finite sum. So let me write it again. And so let me say that is kind of the key idea of this first week. Remember, the theme of the first week is that we have two very different numbers combinatorially, graph counting and Hurwitz numbers. But what I told you, and I wrote it on both days, I think, is both the G and, so the graph counting numbers and the Hurwitz numbers, or rather the generating functions of, satisfy, well, I don't have to say that. They satisfy quadratic recursive differential equations. So if I say it for the coefficients, it's quadratic recursions. This, as far as I know, was not known. Actually, I don't even know if it was known for graphs in this form, this particular calculation. I haven't seen it, and my coworkers hadn't. And for Hurwitz numbers, we hope at least, that wasn't known, because otherwise the whole paper we can throw away, and we don't want to because it's for a specific purpose and we need it. Okay, so both of them satisfy quadratic differential recursions. Well, for the coefficient, it's just recursion. For the generating series, it's a quadratic differential equation. And since it went very far away, and some people are sitting on the left, I'll write it again. So for all g greater than or equal to 0, g2, remember, this is d squared of gg, and that's d to the first. This is the sum g1 and g2 greater than or equal to 0, L greater than or equal to 1, g1 plus g2 plus L equal to g plus 1. And then here, it's 1 over L factorial, g1, first derivative, and g2, L plus first derivative, which is at least the second derivative. Okay, so that is the quadratic recursion, and we'll see that for the Hurwitz numbers, I hope today still, that there's a very similar one. Now, I'm not going to give all the details, but let's do just the beginning, just to see how this gets you into the Lambert space, because in another life, when you're doing Rebin graphs or some Hodge integrals or some problem I don't know about, you may end up with such a quadratic recursion, and then this is how you treat it. So I'll do it in more detail, and I hope today still, for the Hurwitz numbers, but just quickly. So we start at the bottom. That's always the place to start, because the top, it's hard to get to. Okay, so we start with g equals 0. And so what do we have? We have g0, the second derivative, minus g0, the first derivative. And now the only way to add up these numbers to be 1 is 0, 0, 1. So 1 factorial is 1, so I get g01 times g02. So let me call G0 1. Let me call this T. Of course, it's going to be the real T, but we don't know that yet. It's the same as I did before for the graph. So let me call it T. Then what's written here is that d of t minus t is equal to t times d of t. Right? Because t is just a notation for that. This, by the definition, is d of that, so it's d of t. But now you can pull the t over, and so you see that d of t is equal to t over 1 minus t. Which means, since this is an invertible power series, that d is t over 1 minus t, d by dt, but this is already z, d by dz, and so the same argument that we already used implies that z is t e to the minus t, just as we used for the graphs. Same idea. So you don't even have to start knowing about Lambert functions, have the clever idea, oh, let's substitute the Lambert function. No, you take the functions as they come out of the differential equation. The very first equation, well, it doesn't involve g0, 0. So you start with g0, 1, call it t. Then you find a formula for the derivative. And once you know that's a first-order differential equation, we learned in first year calculus how to solve that, and that's the answer. So that's the end of that story, and therefore g0, 1 is t, and therefore g0 itself is the integral t squared over t, and only the second derivative, which would then be t over 1 minus t, that would already be, actually even that's not in the Lambert, no, that is in the Lambert ring, advanced at the origin. So here I have to take the second derivative to get into the Lambert ring itself. This is in the extended Lambert ring. Okay, now if you do g equals 1, then it gets a little more painful. So g12 minus g11 is equal to, and now the sum here is 2. So the only way to get 2 is either L is 2 and the other 2 are 0. So that'll be a half. And then since the other 2 are 0, L is, what did I say? L was 2. So L plus 1 will be 3. Right? That would be, if since g is 1, so 2 could be 2. And otherwise, L has to be 1, and then 1 of g1 and g2 are 0. And since L is 1, there's just a 1. So I'll get g0, 0, g0, 1 times g0, 2. Sorry, one of them is a 1, and the other is a 0 in either order. So with a little luck, you get this differential equation. Now I want to stop on this proof 3 because I want to go on to the Hurwitz numbers where we'll have an exactly similar quadratic recursion, and there I'll show you the rest of the details. But you can at least see that if I'm not lying, then you can at least check what I'm saying, because I told you that g1 is this thing, so therefore g11, as I've written already before, is 1/2 t over 1 minus t squared, I think. And g2 is whatever it is with the 1 minus t to the 4th. And we already know g0, and so you just check that this is true. And in the other direction, this clearly is a unique solution. Just expand it. It's a power series. You'll see that it determines each coefficient. So therefore, I don't have to go through the details. We can now find g1. And similarly, I can find g2 and g3. At each stage, I can check it. But it's not quite obvious that this equation, when you integrate it, is still a polynomial. You know, sometimes when you have a polynomial in 1 over 1 minus t and you integrate, there's some residue which is non-zero, you get a log. So it's not completely clear that you get a polynomial. Also, it's not quite clear that the degree, but believe me, that part is very easy. If you assume it's a polynomial, that part is actually also easy. And it's a top degree, of course, depending on g. So it has some biggest power, d, which I claim is 3g minus 3, and some coefficient c, which is this trivalent graph business. And similarly, the lowest one. You just put that into the recursion, and you expand in this recursion either for t very near 1 or for t very near infinity. Then you get a recursion. And the recursion you get for the b's is a quadratic recursion for the, so if I take this number, the top coefficient, which I call bg minus 1, the top exponent is 3g minus 3, that you prove by induction. And this coefficient satisfies then a recursion, but it's quadratic because everything is recursion. So you get a recursion that bg times something is something times bg minus 1 plus some sum bg1, bg2 for the top coefficient. But this means that the generating function, called beta, satisfies an equation of the form beta prime is beta squared with some coefficient beta and 1. So that's what's called a Riccati equation. beta prime is a quadratic polynomial in beta. That equation determines the betas. But on the other hand, the one that I'd claimed and removed was the log of this sum with the 6m factorial and so on. But that's a purely hypergeometric series. Every hypergeometric series has a trivial differential equation, which is a linear differential equation. When you take its log, you still get a nonlinear differential equation, and when you work it out, it's quadratic and it's the same one. So you see, you do get this way also that it's the true coefficients. So each of these ways lets you pin down the degree, so the growth of the coefficients. This also tells you the growth. If you want, I can write it down. That's kind of a boring point. This tells you the growth of the numbers g, g, d for fixed g as d goes to infinity. It also tells you the leading coefficient and this business with the trivalent graphs. So now I've practically used up all of the time. And so I do want to start in the Hurwitz numbers, but I'll have to continue with them next Tuesday because I didn't get as far. And then later next week, I get into the corresponding problem for coverings of the torus. The Hurwitz numbers are coverings of the sphere. So let me do just the beginning. I don't want to say more about this. If you have questions, wait 10 minutes and ask me after the lecture is over. So I've said enough. I gave you 3 proofs of this. I think I've flogged this horse to the ground, or whatever the expression is. So let me go on to the Hurwitz numbers. So HGD, again, I don't want to get involved in a formal definition. I'll give it probably next time in terms of graph theory. But remember, it was coverings of S2, D to 1, coverings of the surface of genus G, which is given. Could be anything. D is, of course, at least 1. And I want it to be generically ramified, which means that at any point which is ramified, only 2 sheets of the D come together. So the inverse image of any point is either D points, that's generic, or for a finite number of points, it's K minus G. So we have K. So here's my map, and here there are D sheets, but sometimes there's a point where they come together, and so this is a ramification point, or ramification value, I always forget, critical value, and let's say there are K ramification points, and then I hope that I remember the calculation from the Riemann-Hurwitz formula correctly. K is 2G plus 2D minus 2. So if you have this generic ramification, maybe I should check, since there are, after all, it's meant to be a graduate course, not everyone is a topologist. Is this sort of familiar to everybody, more or less, how you relate the number of ramification points to the genus, upstairs and downstairs, Riemann-Hurwitz formula? Well, Motohiko knows, yeah, but I was thinking of the graduate students. Just pulling your leg. OK, so maybe I don't go into that. It's kind of standard, and it's not part of what we're doing now. So I'm fixing the degree, and I'm fixing the genus, but equivalently, you could say, forget the degree, it takes care of itself. I'm fixing the number of ramification points, which have to be at least 2D minus 2 and even, or it won't work. There won't be such a covering. And then I look at these default coverings. So I fix the number of ramification points and the degree, and then the genus takes care of itself. OK, and I want to count those things with the usual method of counting. I don't want to go into it now. I refuse. I will talk next time about how you can see it group theoretically, and then I'll give a correct definition on the algebraic side, which I guess for Hurwitz, or maybe Frobenius, showed was equivalent. OK, so these are the numbers. And so this is the famous numbers of Hurwitz. So Hurwitz wrote a wonderful paper. It's absolutely a beauty to read. You have to be able to read German, but it's wonderfully written. LaTeX hadn't been invented, so it's really nice to read. There's no theorem remark 1.3.9.7.2. He just says things and tells you, and it's a real pleasure. And then 10 years later, 1901, he wrote another paper where he said, I saw that there's a simpler way to get something, and that I'll talk about next time. It's also very beautiful and also beautifully written. Actually, I've read a lot of Hurwitz. He's always a pleasure to read. It's somehow fun and very low-key, but always very beautiful mathematics. So, OK, so there are these 2 papers, and he studies these numbers. And one of the things he shows is that if you fix the degree, like 1, 2, 3, 4, 5, 6, then you get things of given dimension. So let me say what our goals will be, and I'll start doing it. So our goals will be, first of all, we're going to give, as I already said, a quadratic recursion. That I hope I can still do today. For the h's. But I won't deduce it. I'll deduce it from a known recursion in the literature, and I would dearly love to find an elementary direct proof. We haven't succeeded with my two co-authors. We don't see. Easy way, if somebody does, I'll be very grateful. So it will be kind of a black box. I'll show you a recursion that's in the literature. It's complicated. There's no proof. I mean, it's proof, but not by me, and it's a complicated proof. I'll just assume that, but I'll deduce from that complicated recursion a very simple quadratic recursion. And then everything else I do, you don't have to know even what a Riemann surface is. The recursion is a recursion for some numbers. We will study those numbers and show all of the properties. So just from the recursion, just using, so it's completely elementary. It's kind of basically undergraduate kind of mathematics. Just using the quadratic recursion, we will get essentially all of the known properties, some of which were only known by using very complicated things like the ELSV formula and computations of Hodge integrals in moduli space, but now they're just simple fiddling with generating series for half a page if you have this recursion. So we will get lots of things, most of which were known, a couple we think were not known, at least we didn't know. So I'll number them as it was in the paper. Well, first let me write down the quadratic recursion, because since I've just been talking about GG, in fact, I even kept the equation here. That's very convenient because now I can keep the corresponding notation here. So let me make the notations I'm going to use. If you're taking notes, please make sure you get this down. Otherwise, I'll write it again next time. So just as with the graphs, I sum over all G and all D. D is strictly positive, G is non-negative. HGD, sorry, the Hurwitz numbers are rational numbers. So the Hurwitz numbers, as he defined them, are integers, because he, in some sense, labels everything. It's very convenient to divide by the k factorial. Remember, k was the number of ramification points, and you don't want to label them. I mean, you do if you want an integer, but you don't if you want a nice thing with automorphisms. And remember, that was 2g plus 2d minus 2 factorial. So these will be rational numbers, but actually their denominator will turn out to be much, much smaller than that. Essentially, they're going to be in the Lambert space, so actually they will be in 1 over d factorial times almost z, meaning if you fix the genus g, there's just a fixed denominator. So the denominator is actually much smaller than this huge factorial. But for the moment, that's my definition of HGD. And I use that to make my generating function. This, remember, was the number of so just as before, I had x to the g plus k minus 1, g plus d minus 1, which was the number of edges of the graph. Now it's the number of ramification points. It's 2g plus 2d minus 2, y to the d. So it's absolutely convenient to do it like that. Okay, so that's my basic generating function. And I will also call it, so I'll also use hg of z is just the generating function. So in an indeterminate z, it's a power series with no constant term, which we know is the same as sequences, and it will be the sum hgd z to the d. So script hg, so therefore I can also write this, just as we did for the others, as hg of z, which is now x squared y. So this time z is not xy, it's x squared y, but again, d, which is z d by dz, is also the same as y d by dy. All of that's the same. Before, there was only a factor of x, now it's x squared, and then again, it's x to the g minus 1. So this is just setting up notation, which I'll repeat all of this at the beginning of next Tuesday when I go into more detail. So we have the generating function for all of the Hurwitz numbers where you vary both the degree and the genus. And then for each genus g, we have the generating function over degrees. And then the double two-variable generating function is a one-variable generating function whose coefficients are those hg of z, but z is shifted to be x squared y. OK, so now the quadratic recursion. So the quadratic recursion I can now write. Of course, you can write it out in terms of the coefficients. I'll do that next time. But for now, I'll write it. And it's very similar to this. Here we had GG2 minus GG1. Now, in some sense, everything's a little bigger. Remember, the g plus d minus 1 became 2g plus 2d minus 2. So everything's a little worse. And it's this. h3 minus h2 is equal to twice the sum h2 times the sum L from 1 to infinity Oh, sorry, this is for the full generating function. So remember what I just did before. I'd x to the L over L factorial, but now it's only going to be over even numbers. All of this will be explained next time. So this is not quite like that one. It's like the one that I started with, which I raised. So for comparison, remember the one for the full generating function of graphs, the two-variable one, where I don't fix g or g, was g2 minus g1 was simply the sum, L greater than or equal to 1, x to the L over L factorial, times g L plus 1 times g1. So that was the one that we had for graphs, and this is the one we have for Hurwitz. And you see they're exactly of the same nature. In a sense, I could finish now and say you can believe that with the same methods, you can now get the same properties here. And HGD, sorry, did I not write that? I certainly meant to. Well, I drew a picture. I said HGD, and then it's a surface of degree G. So I think the surface of genus G always means connected. Yeah, of course, e to the h, the partition function, we'll also use, but there's no easy function for that. So we will use the disconnected ones next time for something. And also when I talk about coverings of the torus. So you see these two things are extremely parallel. And just as I can make coefficient comparison, I get coefficient comparison here. So we're going to deduce three main things. And at least I want to write them today. And then I'll either stop, or if I still have 1 minute, I'll deduce this recursion from the one that was in the literature. So the first one, the first property says for fixed D, the function h gd, so the function g goes to hgd, is a finite linear combination of pure exponentials m to the power 2g, well, in fact, plus 2d minus 2, but of course d is fixed, that's just a constant, where m, in the other one it went from d to d squared, now it goes from 1 to d over 2, d, the binomial coefficient d over 2, so d times d minus 1 over 2. So e.g., if I take g equals 6, and by the way, the leading coefficient, if I take d equals 6, the leading coefficient is always 2 over d factorial squared. So if I multiply by d factorial squared over 2, it's monic and all the other coefficients are integers. So the full theorem is if you multiply hgd by d factorial squared over 2, it's an integer linear combination of pure numbers, and now I'll call this k is 2g plus 2d minus 2, so I don't have to keep writing it. So here's an example. It's 15 to the k, so it's like the corresponding forms I gave you for graphs. Minus 36 times 10 to the k plus 25 times 9 to the k minus 225 times 7 to the k. There aren't so many gaps, so there are a lot of terms. I'm sorry. But what's nice about this formula, it's what you usually think of as not nice about a result, is that it was already known. Namely, this theorem, P1, was already given by Hurwitz in his first paper of 1891 with the new simpler proof in his second paper. So I should write again, k here is an abbreviation for 2d plus 2g minus 2, which is here 2g plus 10. So in this formula, k is 2g plus 10. I didn't want to write it 20 times. So that, and this one is actually due to Hurwitz. Hurwitz himself in 1891 not only proved the abstract theorem, but he worked out by hand with no mistakes at all up to degree 6. So all of these coefficients, like this 15,200, you can see printed by Hurwitz in his paper. It's quite amazing that he actually got that far. That's why I wrote out, if he didn't mind doing it without a computer, we shouldn't mind. So that was the first kind of generic statement. Now I'm already in overtime, so I'll say P2 and P3 now more briefly. And then next time I'll go into the proof, so that'll be next Tuesday. So that was P1. This also, of course, gives the asymptotics, because obviously when g goes to infinity, This is the dominating term, and that's exponentially smaller. So you get very, very precise asymptotics for fixed D. Then P2 is for G fixed. The function, well, I've said this now 20 times, so D goes to this little hgd times D factorial is in the extended Lambert space. Well, this is if G is greater than or equal to 2, else you need lambda extended. So you have to add, alpha minus 3 and beta minus 1. Okay, so these are all in the Lambert space, and in particular, they're all combinations of any two of them, just as before. So e.g., so any hgd is a combination of the earlier ones, and so I'll give you two of them. Maybe I'll only give you one of them because I'm already in overtime. So again, this Lambert property tells us that if you fix the genus, you get a function of D, and that function is always a combination with polynomial coefficients of the two functions you get for genera 0 and 1. Okay? And then thirdly, which is an easy consequence of all the Lambert machinery, you get an asymptotic, which maybe I'll just say, now I can give it for the original G. There's a constant. I'll give the formula, but it's an integer, which I'll tell you in a second what it is. Cg squared root of pi over 2 over 24 square root of 2 to the G times gamma of 5G minus 1 over 2. So that's a constant depending on G. And then there's an exponential factor 4 over e to the D times d to the power 2d minus 5 plus 9g over 2. So this is as d goes to infinity with G fixed. And so that's the end of that statement, except that I haven't told you what CG is. And so CG, you can say, so G and CG are just some integers, minus 1 to 98, 19,600, and they grow rather quickly. And there's a recursion, a quadratic recursion, and they correspond to the generating function. I'll write it next time. Generating series satisfies a Pandavay-1 equation. So these are some explicit numbers that you can compute recursively. There's a quadratic recursion, which is equivalent to a differential equation, which is Pandavay. But now I don't know a nice geometric interpretation like trivalent graphs. So that's the, but I wanted to show at least the parallelism, and I think it's clear now that the two stories work exactly the same way. The same theorems were true for graphs, polynomial in e to the x over 2. For fixed D, in the Lambert space for fixed G, the asymptotics I didn't write, but there's an exactly similar statement. But they're using the number of trivalent graphs. But that was the solution of a Riccati equation. This is a Pandavay equation. They're rather different differential equations. OK, so I'm finished for today, and thank you for bearing with me.